Hello everyone, welcome to this video. This video is provided by the Offshore Craftsman Society. I am craftsman number 12. In this video, I will share with you how to use WADAM for frequency domain analysis. The software we are using is Hydro-D. For basic frequency analysis, the essential preparation materials are the T1.FM and the mass information, which we will discuss. The main steps of frequency analysis are: first, use Genie to perform standard modeling. Note that here, modeling refers to modeling the wet surface only. After that, you need to attach the wet surface in STDive. Then, create virtual loads on the wet surface. Next, export the T1 file, which is what we refer to as generating the mesh. Then in Hydro-D you need to set the frequency domain conditions, including the wave period and phase, and then set the draft and mass model. Finally, you can complete the frequency domain analysis. Alright, let's begin the operation by first creating a new case file. You can name it whatever you like. After creating the new case, click on File in the upper left corner. Import the XML file I have prepared for you. Alright, this is the model of the hull that we will be using for the frequency domain analysis today. As you can see, it only has the outer surface. We can also see that this point in the middle is the global coordinate system's 0, 0, 0 point. Next, we need to divide the wetted surface of this ship. You can see that the surface of this ship is made up of a series of small transverse surfaces, but now we want to cut it along the height direction, so we select it and then choose Outside Disk. Here we choose to use a plane to cut it, and we set the height of this plane to -2 meters. This -2 meters is the position of our waterline. Then click Apply. After clicking Apply, we find that these surfaces cannot be cut, which may be due to some issues during modeling. That's okay, let's close this for now, and use another method to determine its wetted surface. We can create a plane for it, a real plane, and use the intersection between planes to generate a topological line, which will help us determine its wetted surface. You can follow along with my steps. Alright, I have generated 2 lines at the waterline position. Next, I need to create a plane in the area between these 2 lines. This is our actual water surface. When the water surface intersects with the hull, a structural topological line will be generated on the hull. Next, I just need to delete this water surface. Right everyone, now you can take a look. This short white line is the topological line that was just generated due to the structural intersection. Next, I need to select the entire hull. Then I will explode its surfaces. We select Divide. Choose the command at the very bottom and click Apply. At this point, the surfaces will be divided according to the internal topological lines. Now, we just need to select the surfaces below the waterline. Oops, I selected too many. We can select again. Alright, now the surfaces I've selected are the wetted surfaces of my structure, which are the parts below the waterline. Let me switch the view. Now it only displays the structure of the hull. Next, now that we have the wetted surface, we can set it up. In the Edit Properties menu, find Wetted Surface at the bottom. Alright, I have one here, so I'll delete it. Now I'll create a new one. The name doesn't matter, just click OK. Then I noticed that the surface on the right wasn't selected, so let's select it again. Oops, I selected a bit too much on the right side. Alright, once the selection is done, we can choose the second to last option. Set the selected surfaces as the wetted surface, then select the front part as the direction of water pressure. After turning it off, our wetted surface has been created. Next, we need to create a new analysis. After creating another analysis, we need to assign a virtual water pressure to the wetted surface we just created. Click on Load at the top. Click on Load Case. Remember to check the option for virtual water pressure, then select the wetted surface we just modeled and click OK. Then, in the Edit Properties section, check whether the corresponding mesh properties are present. Okay, I have the corresponding mesh properties here, so next we can start the analysis. Just click this analysis button, and it will automatically generate the mesh for the wetted surface. Sorry, not just the wetted surface, but the entire mesh. After the analysis is complete, we see that it shows warnings here. Warnings are acceptable. If it shows errors, that means there is a problem with the modeling. Alright, let's close this window. Now let's switch the view to see what the inlet pressure looks like. We can see that the orange color represents the corresponding inlet pressure. You can notice that only the wetted surface has this kind of inlet pressure. Next, we can click on File Output to export the finite element file, which is what we refer to as T1. Alright, I usually remove the prefix and keep only T1.fem. Okay, our preparations in the direct translation process are now complete. Next, let's open the HydroD software. First, on the left side in the design tree, select Hydro Modules to create a new hydrodynamic model. Here, keep the default settings and click OK. Then, let's expand Hydrostructure. Under Hydrostructure, we click to create a new panel model. It will prompt you to select a TFM file. We choose the TE file we just generated. My T1 file from earlier is right here. After a successful import, we can see that this is the T1 file we just generated. Once the file is imported, we need to create its frequency domain conditions, which are the wave period and wave direction. Under the Environment folder, we select Directions, right-click, and choose to create a new direction. For frequency domain analysis, generally speaking, we set the direction from 0 to 360 degrees with a step size of 90 degrees. We click Field Table, then click Apply. Next, click on Water to create the wave period condition, right-click. We select New Frequency Site. Then set the starting wave period to 2 seconds. Set the final value to 20 and the step size to 2. Alright, we click Apply. Actually, this part can be set to a longer range if needed. Then we click the Environment folder, right-click to create a new location. Under Z Location, there's no need to change anything. We can just click OK. Then click on Location. In the design tree on the right, we right-click. Create a new translation analysis condition. Alright, after the translation analysis condition appears, We can see that it consists of direction and frequency. These wave direction and period settings are exactly what we just configured. Alright, we click OK. You can see that under location, there is now a new condition 1. This is the translation analysis condition we just set up. Next we click landing condition to create a new landing condition. Here, we need to set the position of the waterline, because when we set the Z gene earlier, the waterline was determined to be at -2 meters, so we need to change the 0 here to -2 meters. Click OK. Alright, now you can see the position of the water surface. The water surface position is now consistent with what was set in the gene. Next, under the newly created landing condition, we need to create its mass model. Alright, let's look at the input methods for the mass model. There are a total of 4 input methods. The first input method is to import from a file, where you select your T1, T2 or T3. Next is user-specified input. Here, you can manually enter its mass and center of gravity, and then there is a matrix. The fourth is to use a simulated body model, which is not commonly used. Today, I will use the user-specified input. Let's just randomly give it a distance between the buoyancy center and the center of gravity, and let it calculate one by itself. As you can see, this is the center of gravity and mass it calculated by itself. Alright, let's click OK. You can see that there's an extra mass point here. I'll hide the water surface for now. This mass point is exactly the position of the center of gravity we just entered. Next, we can create a new WADAM analysis. Let's select New WADAM. Choose the hydrodynamic model, select the loading condition, and then select a condition for frequency analysis. After selecting the third option, we just click OK, then right-click to select. Start running. The frequency analysis has now finished running. Let's close it, right-click, and then select Pose Wrapped. In Pose Wrapped, we first click on Point to define the position of the horizontal axis. Let's change the horizontal axis to period. Change the unit for rotation to degrees instead of radians per second, then click OK, and then click Display. Select Response. Next, what appears is the 6 degrees of freedom motion that we see. The force below refers to the first-order wave force. For example, we can first look at the heave motion T5 in the 0-degree direction. This is the heave row of our ship under waves coming from the 0-degree direction. We can also look at its first-order wave force, for example, the first-order wave force in the surge direction. Okay, if you want to see the added mass and total damping, we can select Matrix to check the added mass. For example, the added mass in the 1-1 direction, which is the surge direction. If you want to print out all this data, we can click Print. Under Print, you can select a degree of freedom and a wave direction. The displayed data can be copied directly, making it convenient for us to paste it into other plotting software, such as Excel or Origin. Alright, next we'll import the model with compartments. Let's switch the view and take a look. These are the 2 compartments. After importing the model, we can proceed directly with an analysis. Once the analysis is complete, we'll export a T3 file. Then let's return to Hydro D. In Hydrostructure, right-click and select to import a structural model, choose the T3 file we just exported, and click OK. Before setting up the compartments, we need to configure some parameters related to the compartments. For example, the first one is deck tank. Deck tank means telling Hydro D which compartments are used for ballast. Next is the filling ratio. For the filling ratio, let's set it to 0.1 for now, which means 10% filled. This can be understood as the compartment being filled to only 10%, but you can also set other filling ratios. For example, 0.5 means 50% filled. Then click OK. Next, we need to set the properties of the liquid being filled. It shows 900 here, but since we're filling it with seawater, it should be 1025. Next, right-click to select the compartment. You can see there are 3 compartments in total here. We will set each compartment as a deck tank. Alright, then we'll delete the middle compartment number 4, as we don't need it. We only need 2 compartments. Then, on the ballast tank, we right-click. Right-click on it. Assign it as ballast water. Then select the fill amount. Let's choose a fill of 0.1 first. If we don't consider damage conditions, we don't need to fill the middle 2. Click OK. You can see that these 2 are the locations of our ballast water. Next, we can right-click and select Civil Report from Bench to check some parameters of the ballast water. Here, an XML file will be exported. We can just give it any name and click Save. Alright, let's open the XML file we just saved and take a look. Here is the name of the ballast tank. Here is the density of the ballast water, and following that are some ballast parameters we need. Now we can do a quick calculation of the mass of these 2 ballast water tanks. Okay, this is the total mass of ballast water for this ship. Next, we need to modify the mass in the MICE model. Because now part of the mass belongs to the ballast water, we need to adjust the ship's mass to be a bit lighter, make it smaller. You can follow along and enter the mass as I do. Now the mass I currently entered is the total calculated mass, minus the mass of the remaining ballast water. You can take a look at the current mass. And this is the mass of our ballast water. Next, let's start the WADAM analysis. After the analysis is complete, we open the history file. Within the history file, we can locate the detailed mass specifications of the vessel's hull structure. Alright, it's right here. We can now see the mass information of the hull. Ah wait, that's not right, it seems to be the one above. Now, the mass information of the hull consists of 2 parts. That is, the mass of our ballast water and the mass we input into the mass model. Only when these 2 parts are added together do they equal the total mass currently in the list file. Alright, next let's look at some issues that might be encountered during frequency analysis. First is the mass model. What is the difference between using a file and manual input? If you manually input the mass model, it is treated as a mass point, and you cannot check the frequency internal force of a specific section. However, it's more convenient to input, as you don't need to prepare an additional T3 model. For example, with this ship, I can create a new load core section on the left side under Load Core Section. You should select the X-plane here. Okay, now I've created a section. After the frequency domain analysis is completed, I can see the bending moment and shear force on this section. But think about it, if your mass model is manually input, meaning it's just a mass point, then a single point doesn't have bending moment or shear force. If it's a stick, you can look at the bending moment and shear force in the middle of the stick, but you can't do that with just a point. That's why the mass model B data needs to be imported from a file. The second question is, when performing frequency analysis, we first need to draw a mesh in Gene. So, how large should the mesh be? Actually, for frequency analysis, a finer mesh is not always better. Frequency analysis does not have very strict requirements for mesh size. For most marine structures, a mesh size of 1 to 2 meters is sufficient. If it is a large marine structure, you can use a 2-meter mesh, and there is no need to refine the mesh at the waterline. However, it is best for the wetted surface to extend above the waterline. For example, we can refer to DNV's RPH 103 standard, which clearly specifies the requirements for frequency analysis. It specifies the length of the mesh diagonal. It should be less than 1/6 of the minimum wavelength. The third issue is how to generally select the wave period and wave direction. This depends on the specific situation. If your structure is symmetrical, and if there are many grids, to save time, you can select only some grid wave directions and wave periods. Generally, you choose between 2 and 30 seconds, with an interval of 1 second. If the interval is any smaller, it doesn't really make sense. If you want to import the generated G1.sf file, which is the G1 file produced after your frequency analysis, into SEMA for time domain calculation, you need to manually add the 360-degree data. For example, in HydroD, we have enabled the wave direction. I set the step size to 30 in the field table, and at this point we will notice that the 360-degree wave direction has disappeared. This is because in HydroD, it treats 0 degrees and 360 degrees as the same by default. If we change the step size to 90, we will also find that there is no 360-degree entry here. So, we need to manually add the 360-degree data. After adding it, we can look at the lower left corner here. You will see that the 360-degree entry is present, and that's fine. Next, what is the difference between the global coordinate systems in Genie and HydroD? Everyone can take a look at this diagram. The coordinate system shown below is the input coordinate system, which can also be understood as the Genie degree coordinate system. The projection of Genie's coordinate system onto the water surface gives us a new coordinate system. This new coordinate system is the global coordinate system in HydroD. Therefore, when modeling in Genie, for convenience, we can directly place the waterline at the origin, 0 point, of the global coordinate system. That is, when the global coordinate system's z equals 0, it corresponds to the waterline. In this way, the coordinate system in Genie is the same as the coordinate system in HydroD. The fifth question is, the results of the translation analysis are referenced to where? The rotational moment of inertia is with respect to the origin of the HydroD coordinate system, which is the origin of this new global coordinate system, not the origin of the original input global coordinate system. Another question is how to account for viscous damping of the hull in HydroD. You can add an additional damping matrix, and the value of this damping matrix can be set between 2% and 12% of the critical damping. The specific value depends on the shape of your structure. You can first conduct a model test, or refer to empirical values from other people's papers. Next, can a mooring system be added in HydroD? HydroD itself cannot model the mooring system, but you can use an additional force. Or you can use a restoring force matrix to simulate the mooring system. You can add a damping matrix under the additional matrix option in the loading conditions section. For the damping matrix generally, you only need to input the 6 diagonal elements since they are directly related to the motion of the floating body. This will also affect the results of your response analysis. Alright, you can also add a restoring force matrix. This restoring force matrix represents the mooring system. It is used to simulate the restoring force generated by the mooring system. For example, in the report on OC4 published by the National Renewable Energy Laboratory in the United States, the restoring force matrix for the OC4 wind turbines mooring system is provided, which you can refer to. Furthermore, if you need to discuss advanced topics such as using program control for batch simulations or plotting, conducting multi-body coupled response analysis, or further developing secondary functions for Orcaflex, feel free to send me a private message. Thank you everyone.